Good afternoon. I'm Dillon Jackson, and my capstone project is titled Mapping Host Forensics to MITRE Attack for Incident Response. Here's an overview of the presentation. Host-based forensics is one of the least standardized parts of incident response. Investigators often rely on whatever an individual analyst happens to know, which means indicators get missed and containment gets delayed. This matters for two trends. First, breaches are taking a long time to contain. IBM's 2025 report puts the average at 241 days. Secondly, as nearly all network traffic moves to TLS encryption, packet inspection is giving us less and less. So the host itself, its logs, registry, scheduled tasks, and processes have become the primary source of forensic evidence. The gap I'm going after is that existing frameworks are good at telling you what phases an investigation should have, but they stop short of connecting specific host artifacts to specific adversary behaviors. This project takes the first step towards closing it, showing that a focused set of APT29 techniques, the connection can be made reliably. The literature breaks into three areas: NIST, the Incident Handling Guide, and the Cybersecurity Framework. It gives us a solid lifecycle structure, but no host-level procedural detail. MITRE ATT&CK and the APT29 profile give us a rich taxonomy of techniques, but that taxonomy rarely connects to forensic artifact collection. And tooling like Atomic Red Team, VirtualBox, and Security Onion let us reproduce and test adversary behavior safely. Each of these is well developed on their own, but something that's missing is a unification of all three into a single methodology or workflow. My approach has four moves. So the first is to bridge the high-level incident response frameworks with concrete host-level procedures, then map every investigative step directly to a documented APT29 technique. And then the instrument is the host with endpoint telemetry and centralized logging, and then validate the whole thing in an isolated lab using Atomic Red Team to emulate the adversary. The guiding question throughout this was, given a Windows endpoint suspected of compromise, which artifacts should an investigator collect, and in what order to confirm or rule out a technique? The design is artifact-driven, not alert-driven, and that matters because once we're inside an investigation, we don't stop at whatever detection happened to fire. We look for the specific evidence a technique should have left behind, whether or not anything alerted on it. The flow runs from the Windows endpoint where sysmon and the Windows event logs capture activity, and then it's forwarded through Elastic Agent into Security Onion, where Elastic and Kibana index everything. The final layer is the mapping itself, taking each artifact and tying it back to an APT29 technique. Implementation has four steps. Build the isolated VirtualBox lab with Security Onion. Configure logging so sysmon and the events logs feed directly into Kibana. Emulate the adversary by running Atomic Red Team test, map to APT29. And finally, collect the resulting artifacts and map them back to the MITRE ATT&CK framework. With the lab running, I exercised 3 APT29 techniques across the kill chain and pulled the artifacts each one generated. Those span process execution, command line, and PowerShell activity, persistence through run keys and services, scheduled task, network connections, and registry writes, each tied to a specific sysmon or Windows event ID. Analysis focused on 3 techniques, chosen because each draws on a different telemetry source. So I could test the approach across process, registry, task-based evidence rather than just one artifact type. I just wanted to clarify, when I say full match, I mean the artifacts I observed lined up with the artifacts each technique was expected to produce, so I could trace evidence all the way back to the attack technique. So PowerShell execution, I used test 1059.001. and it was a full match. Process creation, the script block logs, and the command line were all present. Registry run keys, it was a full match as well. Sysmon event 13 captured the persistence right and even auto-tagged the attack technique in its rule name field. Scheduled task persistence was a full match with event ID 4698 capturing the complete task XML confirmed by the process chain. Five findings. So attribution worked. All three techniques produced artifacts that mapped cleanly back to the correct attack technique. 2, multi-source validation. No technique relied on a single source. Every one was confirmed by these two independent sources, so a single logging gap wouldn't bind the investigation. Monitoring scope limits. 2 artifacts didn't show up, a registry write on a non-persistent path and a task file, but both were deliberate boundaries in the Swift on security config file I used. No failures, and alternative sources still confirm the attribution. Endpoint protection was an artifact gap. When I ran the T1059 test, a PowerShell-based Mimikatz invocation, Windows Defender blocked it before it ran, so it produced no artifacts at all. That's different from a monitoring gap, which would mean that the artifact existed, but it wasn't captured. So this just means that it was never, the logs for this were never real. They never existed, so they were never forwarded. And then lastly, analysis context matters. The same event codes show up for different attacks, for both attackers and legitimate admin activity. So the approach tells you that, it tells you where to look, but it doesn't replace human judgment. The key takeaway was that running known APT29 techniques in a controlled lab, I was able to trace the artifacts each one produced back to its attack technique using independent telemetry sources to corroborate. The point isn't that I can identify an unknown technique from scratch, it's that I've shown the mapping between the technique and artifact is real and reliable. It's important to consider that this was 3 techniques in a controlled lab, so what it establishes is just foundational validation towards a repeatable, evidence-driven investigative playbook, not a finished framework. Future work, so 4 directions follow directly from those scope boundaries, expanded to more tactics like lateral movement, credential access, command and control. And then running the techniques by hand as a red teamer instead of scripted emulation to see if the approach holds when artifacts fall outside of predictable patterns. Vary the telemetry configs to test how much logging and coverage you actually need, and then extend it beyond Windows to Linux and macOS. And then here is the demo.
Hello, I am Dillon Jackson. Before executing anything, I'm in Kibana Discover with a query targeting sysmon event IDs 19, 20, and 21. The event codes associated with WMI subscription activity. No results. This is the clean baseline before any adversary activity. Let's run the test and see what gets generated. Here, I'm executing the atomic red team test for T1546.003. Persistence via WMI event subscription, specifically the command line event consumer variant. Before running, I used the get details and check prereqs functions to review what the test does and confirm the necessary dependencies were in place. The test exits with code 0, meaning it completed successfully and the subscription was registered on the endpoint. Now back to Kibana to see what sysmon captured. Switching back to Kibana, the same query now returns 6 events. While I do have a filter applied for event IDs 19, 20, and 21, those were the only logs generated during the window of execution. The filter didn't hide anything, it just scoped the view. The controlled lab environment makes it easy to rule out noise. In an enterprise environment, these same event codes could be buried in thousands of legitimate operations, making detection significantly harder. I'll start with event ID 19. the WMI filter registration. This shows the attacker defining a trigger condition, a WQL query that fires when system uptime falls between 240 and 325 seconds. In other words, this persistence mechanism activates automatically on every reboot, roughly 4 minutes after the system comes back up. That's the trigger. Next is what it actually does when it fires. Event ID 20 is the consumer registration. This defines what happens when the filter fires. The type is command line and the destination is notepad.exe. In a real intrusion, this would point to a malicious payload. The consumer name matches the filter, which is how we know these two objects belong to the same persistence mechanism. The filter knows when to fire and the consumer knows what to run. The last piece is what ties them together. Event ID 21 is the binding event. The filter and consumer are explicitly linked here. This is the moment persistence becomes active on the endpoint. You can see both the consumer and filter referenced by name in the same event. 3 artifacts, 3 independent sysmon event codes, all generated within milliseconds of each other. And each one maps directly back to T1546.003 in the attack framework. This is the artifact-driven investigative workflow the project is built around.
And then I just have my references and Q&A.
Thank you, Jackson, for your presentation. We'll now open the floor for questions. So does anybody have any questions for Jackson, Dillon?
This is Vijay. For Atomic Red, those testing was isolated based on because Windows was blocking the Windows firewall was blocking the actual test, simulated tests.
It blocked Mimikatz.
Oh, I see.
Yeah. Which makes sense. I mean, Windows Defender should block that, right?
Yeah.
Any other questions for Jackson, Dillon?
Not for me. Good job, Dillon.
Thank you.
Okay.
All right.
Thank
I'll
you,
stop the
Jackson.
sharing. Thank you.
Yeah. Thank you, Jackson, for your presentation. Now the next